Hello everybody, welcome to another online lecture for general chemistry. And in today's online lecture we're going to be talking about ions, how ions form, and basically how we can predict the charges that we're going to associate with an ion based on using the periodic table. So let's go ahead and get started with this lesson. So first of all, what are ions? Ions are simply elements that are taken on a positive or a negative charge, and they're no longer neutral atoms. So a lot of times when we're doing our protons, neutrons, electrons, we're looking at the neutral atom, or for that element, the neutral form that that element would take if it were an atom. So once we're dealing with ions, we're talking about giving a charge to those elements or those individual atoms. Now, there are things that are called polyatomic ions, which have groupings of atoms, and they will have a single charge on them. So, for instance, SO4 has a charge of 2 minus, and it comes as that whole group, a sulfur with 4 oxygens. But we're not going to talk about those until a different chapter, so we're going to get to that a little later on. For right now, let's focus on the monoatomic ions, meaning single atom ions, or the ions that are coming from single elements on the periodic table. So we mentioned ions can have a positive or a negative charge. There are specific terms that we utilize when we refer to the type of charge that is associated with an ion. Anytime we have a plus charge, it's going to be called a cation, and anytime we have a negative charge, it's going to be called an anion. So cation and anion for the plus and minus respectively. Now these are general terms. So the chemistry universe is full of all sorts of cations and anions. The term cation refers to any element or any ion that has a plus charge associated with it. So even if it's 1 plus, 2 plus, 3 plus, etc. And same thing for an anion. Any ion that has any type of minus charge, no matter the magnitude associated with it, is going to be called an anion. So now one of the other important things that we're going to want to note is that ions are specifically dealing with a loss or a gain of electrons. And so proton and neutron numbers are not going to be altered when providing the ionic form, so to speak, of an element. So when we dealt with isotopes, we were talking about changing neutrons. But here, when we're dealing with ionic states, which sometimes they call oxidation states, okay? But when we're dealing with the ionic state of these elements, we're not going to be touching the protons or the neutrons. We're going to be changing the electrons of the element. And so because it's only the electrons that are changing, we have to associate that with the plus and the minuses that we are assigning to each of these elements. So one of the areas that many students tend to get confused with is when they're assigning a plus or a minus, they're trying to determine whether it was a gain or a loss of electrons. And this can be a bit counterintuitive when you're first getting used to it. So let's think about this. Electrons have a negative charge associated with them. And so any time that I'm going to give an ion a negative charge, what I'm really stating is that it gained electrons because electrons have a negative charge associated with them. And any time that I create a cation, which would be the opposite, with a plus charge, I'm telling you that the atom or the element has lost electrons because electrons are normally negative. So if I give it a plus charge, I'm saying, hey, I've lost some of that negative property. So the real plus and minus comes in the proton to electron ratio. In a neutral atom, they're equal. And so if I start taking away electrons, I have extra protons left in the nucleus, and they're going to start creating plus charges. So there's a uneven balance of the plus to the minus then, okay? So a plus is a loss, a plus is a loss of electrons, and a minus is a gain of electrons when we're dealing with this here. So make sure that you're careful with that whenever you're assigning plus and minus, that you actually know what you're talking about in terms of electrons either being gained or lost. Okay, so when we assign an element to an ionic state, any element, nitrogen, oxygen, fluorine, things like that, we are doing this in order to fill their valence shell completely with electrons. And the reason we sort of do this, there's two major reasons, but the first one is filling the valence shell with a complete set of electrons is going to have a stabilizing effect on an element. So the elements, they have these valence shells, and they like to go around, sort of imagine them as like collectors, right? If you have a hobby, they like to collect electrons. and it's going to be very stabilizing for them if they collect the full set of electrons that belong in that valence shell. They don't want any incomplete collections, so to speak. Okay? And so one of the reasons that we do this is to help understand the stability. The ion that we form is going to be the most stable ion possible because they're going to try to fill up all the electron slots that they have in the current valence shell that they're in, or they're going to try to retreat back to the former valence shell, which we'll talk about. Okay? So another reason that this is important, which will become more apparent in later chapters, is that when some compounds will form or break apart, particularly if they're going to break apart, they're going to break apart into cations and anions. So I have something, for instance, sodium chloride, and the sodium chloride comes apart into its ionic forms. I'm going to have Na and Cl, and I need to be able to assign charges to those when they come apart from the original sodium chloride molecule that I was looking at. And in order to predict the ions that are going to form when these compounds break apart, we have to know what the most stable ionic form of each element would be in that case. So some of this is going to, again, make a bit more sense in future chapters when we start to talk about creating and breaking apart ionic compounds. But just hang in there. I promise that all of this is with a purpose, so to speak. Okay? So this all leads to the question, how do we predict the charge of an element? So we're talking about it, we know cations, anions, but that's great. If I set down a periodic table and I get ready to look at it, how can I pick one out at random and be able to tell you what the charge is going to be for that element? So we are going to start with the main group elements, which is the A groups, 1A, 2A, 3A, and we're going to go through the periodic table. We're going to exclude at this point in time what's called the transition metals, which are the metals that are found sort of in the middle of the periodic table. They're a bit more complex. They can take on multiple charges depending on what's called their oxidation state. So, for instance, iron can be 2 plus or 3 plus. So it's not quite as easy to just always predict, oh, iron will always have 2 plus or something like that. So we're going to ignore those just for the time being. We're going to work, let's master the group A elements to start with. So we're leading up to the question, how do we predict the charge of an element? And the answer is going to lie in a group on the periodic table that we refer to as the noble gases. And so hopefully most people know, if we pull up the periodic table here, let's take a look. If we look at this here, we have the periodic table. The noble gases are all the way to the right here. Okay, and what's so special about the noble gases? If we get to the end of each row, we find the noble gas, and we said each row is a valence shell. So when we get to the end of these rows, we have a full valence shell, and then when we go down to the next row, we are opening up or starting a new valence shell that's either going to need to be completed, or we're going to need to get rid of that shell and retreat back to the previous valence shell when we are assigning these charges based on electrons. So, again, each row that we come across horizontally on this table is considered a valence shell. So the end goal of making an ion is to obtain a complete valence shell by any means necessary. And the element can do this in one of two ways. It can either lose electrons, and if it's losing electrons, it's retreating back in an attempt to retreat back to the previous completed valence shell, or it can attempt to pick up extra electrons and complete the current valence shell that it is in. And so for an example, let's consider the second row here, okay, and determine the charges that we would assign to the ion forms of the elements. So we're looking at lithium, beryllium, boron. We're going to go through this whole second row here, all right? So what we want to look at is, what are the two valence shells that are closest to this entire row? Well, to start, we have one valence shell at the end of this row. So if I go all the way to the end of row 2, I'm right here with neon. And if I go all the way back through the second valence shell back to the first valence shell, I'm up here with helium. And so those are the two closest valence shells that are completed that I want to attempt to mimic with all of my ions when I form them. So the easiest way to think about this is, when you're going through, charges are not particularly stable things, okay? And so we don't want to rack up huge charges if we don't need to. We're going to take the minimum amount necessary to complete our valence shell or our collection of electrons, and we'll be done with it. We'll be in a stable state. So let's start on the left here and work our way through. So here's lithium, Li, okay, atomic number 3. I have two choices. I need to either get to helium or neon, okay? My first choice is that I can go and I can collect electrons until I hit neon. So if I'm at lithium, let's look here. How many electrons do I need to count? 1 electron is at beryllium, 2 electrons, and I'm at boron, 3 for carbon, and so on and so forth. So I go 4, 5, 6, 7 until I get to neon. So I would need to have a 7 charge, and what charge would it be if I'm gaining electrons? A minus charge. So lithium could be 7 minus, because it would need to pick up 7 electrons to get to neon, or my second option is that I can retreat backwards. And so lithium can get rid of 1 electron, and then it has the same amount of electrons as helium. And so therefore helium's a noble gas, and the question is, which one is easier or which one is more beneficial for the atom, to lose 1 electron or to gain 7 electrons? And the answer hopefully should be, if you know your numbers and which way you're going, that it would much rather take on a +1 charge than a 7 minus charge. And so we're going to follow this across. Beryllium could either have a 6 minus, it would have to pick up 6 electrons, or it could retreat back and lose 2 electrons to helium, and so we have 2 plus. Okay? So between those two, beryllium 2 plus or beryllium 6 minus, which one makes more sense? Hopefully the 2 plus does. We go to boron, we can be 3 plus or we can be 5 minus. Why 5 minus? Because if I go carbon is 1, nitrogen is 2, oxygen is 3, fluorine is 4, neon, my noble gas, is 5. So boron could be 5 minus or it could be 3 plus. Why 3 plus? Because if I lose 3 electrons, imagine that I'm at boron, I lose 1 electron, I go to beryllium, I lose 2 electrons, I go to lithium, and then I lose 3 electrons and I'm at helium. So again, 3 plus, better than 5 minus. Now, group 4A is a little bit more complex, and I personally, I don't know what your instructor might do if you are not in my class, but I personally am not going to be questioning you a whole lot in terms of group 4A. And the reason is we're right in the middle. So I could be 4 plus or I could be 4 minus in order to reach neon versus reach helium. And so this is a bit ambiguous. Now, you can find carbon as a 4 plus or a 4 minus when we talk about its oxidation state, depending on what it's bonded to. But that's a little more complex in the scope of our class, and we'll get to that at some point, but we're not going to talk about that in this lesson. So just know that in group 4A, we're right on the teetering point. 4 plus or 4 minus would be an acceptable answer at this stage of the game. Okay? Now, here's where we go to the next stage. For nitrogen, if you look here, I'm in group 5A. So nitrogen can either gain 3 electrons, 1 electron is oxygen, 2 electrons is fluorine, 3 electrons is neon, or it could lose 5. Carbon is 1, boron is 2, beryllium is 3, lithium is 4, helium is 5, and we're at helium again. Okay? And so now nitrogen is either 5 plus or 3 minus. Again, remember, plus and minus, gain and loss when we're looking at these. Okay? So when we're talking about minus, we're talking about the gain of electrons. So 3 minus is more beneficial than 5 plus. And so nitrogen would normally take the shortest route and collect 3 electrons to get to neon instead of giving out 5 electrons to retreat back to helium. And so hopefully you guys see the process here. Oxygen is going to be 2 minus instead of 6 plus. Fluorine is going to be minus, which the 1 is implied. But fluorine is going to be 1 minus instead of 7 plus. And then what about the noble gas itself, neon and helium? If you are in a noble gas state, you would not form an ion because you are already at a full valence shell. You're not looking to get rid of or collect any extra electrons because that would ruin the valence shell state and push you into a new shell or back further into the shell you were in, and then you'd have to go around and collect more to become a noble gas again. So the noble gases, by definition, are going to be stable because their electrons are completely full when we look at their valence shell. And so those would have charges of 0. So hopefully this makes sense, okay? And then if I restart, if I go back down to the next line, if I look at sodium, sodium is going to have a plus charge again because, again, if I'm looking here, neon is 1 away from sodium, so +1, and I'm at neon, or I'd have to collect 7 electrons to get to argon. And so what's better, a plus charge or a 7 minus charge? The plus charge. And so sodium takes on a plus charge instead of a 7 minus charge. Okay, so I'm going to bring this up here. Here are a couple examples, and I want you to try to test yourself. So what you should do, pause the video and pull up a periodic table. See if you can assign the charges to these without looking it up online or anything, and then we'll look at these here in a second. I'll put the answers up in a second. So go ahead and pause the video. Okay, so I am bringing up the answers here. You can check yourself on these. Hopefully you were able to get all of the right answers when you were attempting this with your periodic table. If you're still having trouble, watch the video lecture again. Continue to attempt this. You are welcome to send me any sort of questions that you have, and I will attempt to answer them. Okay, so other than that, that's it. Please remember to like the video if it was helpful. Feel free to leave comments if you have questions, if you found this helpful. I encourage you to comment and to be active in the forum in the community. And then other than that, just go ahead and hit the subscribe button if you're interested in being updated when my videos come out. And I will see you guys for the next lesson. Thanks for watching.